In this lecture, we will learn about chi-square distribution and its relevance to data analysis. Let's start by understanding what is a chi-square distribution. Let's go to Mini tab and play a little bit with data. So here we are in Mini tab and I have in these 4 columns some data. So what kind of a data have I generated? I have generated standard normal data, which means I have generated data which has a mean of 0 and a standard deviation of 1. And like this, I have collected 500 rows of data. I assume each one of these columns to be a sample. This is very similar to what I did with central limit theorem. But now, instead of just going and finding out their average as we did in central limit theorem, now I am going to square these values. So I am going to take x1 and square that and put it here. And likewise, I am going to square x2, x3 and x4. All these squared values are given in columns 28 through 31. Now I am going to add all these squares. I am going to add column C28 through C31 and put that in C33. So this I am calling it as sum of the squares. Now I am going to plot a descriptive stat of this. So I'm going to go to graph, I'm going to go to histogram and I'll click on simple and I'll select sum of squares and I click on this. I've got a distribution like this. It starts right from here, it goes up and then it comes down. How many samples did I have in this data? Just to make sure we are on the same page, we had 4 samples for each row, each trial, and if sample size is 4, then my degrees of freedom would be 3. This is what we call as a chi-square distribution with degrees of freedom 3. If I were to summarize what we did just now, any process with any parameter such as a cycle time, if that is normal, then you convert that into a standard normal variable, which is also something that we covered right at the beginning. Then we find out the sum of the squares of that standard normal variable. Whatever data that we get, the sum of the squares would form a chi-square distribution. In simple words, if my factor is x and I do x square, that's called as a chi-square distribution. A chi-square distribution is again a family of distributions, and you would see in the graph below that as the degrees of freedom changes, the shape of the chi-square distribution also changes. And you would realize that as the degrees of freedom increases, chi-square distributions become more and more symmetrical. But for lower degrees of freedom, the chi-square distribution is always right skewed. So what is the application of chi-square? What's so unique about this chi-square distribution, right? So it's great to know that I took some values, I squared those values, and then I plotted a distribution, and now I call that a chi-square distribution. So what's so great about it? The biggest principle or leverage for a chi-square distribution is that it can be used for characterizing or analyzing dispersion of any data. Why? Because what we have done is we have taken a parameter and we have found out the square of that parameter and then we have plotted a distribution. Isn't that exactly what we do when we want to compute the dispersion of any process? We take the mean and then we find out the difference or the dispersion between the mean and the absolute values and we square that. And that's how we get variance, right? So when you divide it by sample size, that becomes the variance. So we are almost doing the same stuff here. So we are computing the sum of squares here, which means this can be used to study variance of any process. If I want to study the variance, if I want to fit one data to another data and find out if my original data is same as the previous data, then I can use chi-square. That is what we call as a goodness of fit test. When we go a little deeper, we will cover this chi-square test in greater detail. Another big application of chi-square distribution is in discrete data. We can approximate the chi-square distribution for discrete data as well, and we can use it to compare the dispersion or the deviation between any observed value and expected value. The difference between observed value and expected value can be compared to find out if my observed value is conforming with my expected value or not. In both these cases, some way or the other, we are studying deviation or dispersion. So what we do is we take the dispersion and we square that, and then we can do a goodness of fit test, or we can do a contingency table and then do a chi-square test for discrete data. In a nutshell, a chi-square distribution has a far-reaching application than any other sampling distribution that we have in statistics. So what are the properties of a chi-square distribution? A chi-square distribution like our t distribution has only one parameter, which is epsilon, the degrees of freedom. Mean of the data is equal to the degrees of freedom, and the standard deviation of the data is square root of 2 into the degrees of freedom. In fact, if you go back to the sample data that we generated, you may be able to confirm that. If you look at this data, we have a mean of 3.7 and a standard deviation of 2.6, and we had a total degrees of freedom of 3 here. So your mean is close to that, and your degrees of freedom into 2 would mean 6, and square root of 6 is also close to 2.6. So that is one of the most important properties of a chi-square distribution. Always remember that chi-square values will be positive. And as the degrees of freedom increases, chi-square distribution will tend towards a normal curve, as I described earlier and as you see in the illustration. Here is the formula for computing the confidence interval for variance. Because our chi-square distribution is not symmetrical distribution, unlike our t distribution or z distribution, the lower limit and the upper limit will not be exactly symmetrical. One of them will be smaller and the other will be larger. So the CI will not be symmetrical on both sides. That is something that you should remember as far as the confidence intervals for variance is concerned, because chi-square distribution is not symmetrical distribution. Let's take an example. The standard deviation of a process is 0.86 and it is ascertained using 12 samples. At 95% confidence level, I want to know what is the standard deviations intervals. So let me go to Minitab and compute this. So here I am in Minitab. I go to stat, I go to basic statistics, and I go to one variance. I click on this, and then I have my sample standard deviation. So I'm going to click on the second option, and then my sample size is 12 and my sample standard deviation is 0.86. And I want to find out at 95%, so I'm not going to disturb that, and I'll click OK. Here right at the bottom, I obtain the confidence interval for the standard deviation. Its values are anywhere between 0.609 to 1.460, while the standard deviation in itself for the sample is 0.86. That way, we will be able to use Minitab to compute confidence intervals for standard deviation of any sample data. With that, we will wrap up this lecture.